Hello friends, let us now learn some important points about the K-edge filters or heavy metal filters. The development of high intensity screens and high capacity X-rays have made it reasonable to consider the use of heavy metal filters. So these filters use the K absorption edge of the elements with atomic number more than 60, and thus they offer advantages when imaging barium or iodine. Thus, it uses K absorption edge of elements with atomic number more than 60. So, development of high intensity screens and high capacity X-rays made it reasonable for using these heavy metal filters. So, let me draw a table showing the atomic number and K edge of the filters. So, if you see, this is the table of K edge and the atomic number with K edge. So, this table lists some heavy elements that have been investigated as filters, and we can compare them with aluminium, iodine and barium. So, aluminium has a K edge of 1.6, so certain K edges are present for all of each of the elements. So before we go into this, let us first understand what a photoelectric effect is and what is K edge. So when an X-ray photon strikes the inertial electron, the inertial electron is released as a photoelectron. So this photoelectron, when it is released, a hole remains, and this hole is filled by the positive charge from the K shell, L shell or M shell. So the X-ray photon which is present here, this should have an energy which is more than the K shell binding energy in order to the photoelectron to released. In order to release the photoelectron, it should have an energy more than the K shell binding energy. So here if you see, the K edge of all these are given. So photoelectric effect or attenuation occurs, or it does not occur at if the X-ray energy is less than the K shell binding energy. So photoelectric effect does not occur if X-ray energy or a photon energy is less than K shell binding energy. It occurs greatest when X-ray energy is equal to or slightly greater than the K shell binding energy or K edge. So it decreases as the energy increases from the K edge. So if 45 kilo electron volts is the K edge, so there is no, sorry, if 45 kilo electron volts is the K edge, no X-ray absorption occurs below the K edge, and just at the K edge or slightly above, slightly more than the K edge, the X-ray absorption or photoelectric attenuation will occur maximum, and slowly it decreases as the energy increases more than K edge. So this is photoelectric attenuation. So if you see the Compton reaction will increase below the K edge, or we can say number of X-ray photons that are transmitted. So number of X-ray photons that are transmitted increases is the number of X-ray photons that are transmitted increases over here, and slowly it becomes 0 at the K edge, and again the number of X-ray photons transmitted will increase. So thus let us begin by reviewing the absorption characteristics of iodine and barium. The reason why we use iodine and barium as contrast agents, and the contrast is greatest when the contrast agents absorb X-rays most efficiently. The maximum contrast is obtained when the photon energy of the X-ray beam is more than or slightly more than the K absorption edge of the absorber in question. So photoelectric attenuation. So the iodine and barium mainly acts by photoelectric attenuation. So maximum contrast is obtained at photoelectric attenuation at a photon energy slightly greater than or above the K edge. The maximum contrast is obtained when the photon energy of the X-ray beam is close to or slightly above the K absorption edge of the absorber in question. So, for example, if K absorption edge of iodine, the mass absorption coefficient of iodine is 6.6 centimeters per gram, just above the K edge. So, this is below the K edge. Just below the K edge, the mass absorption coefficient of iodine is 6.6 centimeters per gram, centimeter square per gram. Then just above the K edge, the mass attenuation coefficient will raise to 236 centimeters square per gram. For iodine, the K edge of iodine is 33.17 kilo electron volt, and and the K edge of iodine is 33.17 kilo electron volt. So at 33.17 kilo electron volt, the mass absorption coefficient of iodine is around 36 centimeter square per gram. So mass absorption coefficient increases or becomes maximum at or slightly above the K edge. Similarly, the K edge of barium is also given. The K edge of barium is 33.45 kilo electron volts. So, if you see, this will illustrate that as the attenuation decreases below or and above the K edge and has a relatively maximum attenuation immediately above the K edge. So, attenuation decreases both below and above the K edge, but has relatively maximum attenuation immediately above the K edge. The purpose of these heavy metal filters is to produce an X-ray beam that has a high number of photons in specific energy range. And these will be most useful in diagnostic radiology. An immediate question may be, what is wrong with our standard aluminum filter? The in standard aluminum filter, the the energy spectrum transmitted by aluminum filters is too wide. The K edge of aluminium is 1.6 kilo electron volts, and the energy spectrum is around 10 to 75 kilo electron volt. K edge of aluminium is 1.6 kilo electron volt, which is too low to be useful as an energy selective filter for diagnostic radiology. So thus aluminium filters are not used for has heavy metal filters, and they transmit radiation or main broad Bremsstrahlung radiation. They transmit broad Bremsstrahlung radiation. So let us now draw a graph. But before that, even we will see about gadolinium filter also. Gadolinium filter is very important. The gadolinium filter is a type of heavy metal filter with thickness of 0.25 millimeters, because it is most thoroughly studied of many of the heavy metal filters. Notice that the gadolinium filter transmits increased number of photons from 25 to 50.2 kilo electron volts. We will see this with the help of a diagram. Gadolinium has an atomic number of 64 and K edge is 50.2 kilo electron volts. So the gadolinium filter will attenuate X-rays at or above 50.2 kilo electron volts, and they transmit the energy from 25 to 50.2 kilo electron volt. So the mass attenuation occurs at or above 50.2 kilo electron volt by photoelectric effect. So if you see, the gadolinium field transmits increased number of photons from the energy range of 25 to 50.2 kilo electron volts. Immediately above this 50.2 kilo electron volt, mass attenuation coefficient of gadolinium increases dramatically, and number of transmitted photons is correspondingly diminished. This heavy metal filter transmits significantly narrower spectrum of energies than aluminium, with decreased number of both high and low energy photons. There is also reduction in low energy photons will decrease the absorbed dose of the patient. Image contrast will be improved by the reduction of high energy photons. That is, more photoelectric effect occurs here and less Compton reaction occurs here. Because of increased beam filtration, there is increased X-ray tube loading and this is required. So, because of increased beam filtration, there is increased X-ray tube loading is also required when heavy metal filters are used. So, if decreased beam photons will increase the beam filtered. So, if you see here, if 50 kilo electron volts of energy is X-rays are penetrated through the filter, the high energy photons, low energy photons are not absorbed by the, are absorbed. Low energy photons are absorbed by this filter, and low energy photons cannot transmit the filter, whereas high energy photons are not absorbed and they are not absorbed completely. Somehow a part of it is absorbed and the rest of the radiation can travel and they can travel through the filter and they can reach the patient. So there is increased exposure energy is seen because this filters will cause some loss of 10 kilo electron volt. So for the patient, in order to receive this 50 kilo electron volt, we should increase the dosage of the patient to 60 kilo electron volt. So because of increased beam filtration, there is increased X-ray tube loading, meaning that more milliampere second is required when the high metal filters are used. But the patient dose, the dose which is given to the patient is reduced by 2 and milliampere second increases by a factor of 2 or more. Patient dose is reduced by a factor of 2, whereas milliampere second increases by a factor of 2 or more. So, improved contrast with a gadolinium filter has been shown maximal with thin body parts, while the need for more milliampere second has been minimized by use of low kVp techniques. So, thus the heavy metal filters may prove more useful. The heavy metal filters may prove to be more useful for pediatric applications when compared to adult applications. Because if there is thinner body parts, there is improved contrast. The improved contrast of gadolinium filter is used in thinner body parts, while then the need of more milliampere second can be reduced by low kVp techniques. So this suggests that heavy metal filters are more useful in pediatric conditions where both kVp techniques and milliampere second can also reduce. Then if you see the diagram showing the relative number of photons with the photon energy. First, if you see, this is the photon energy. We will see both normal aluminum filter and gadolinium filter. So, this is the aluminum filter. This illustrates 2 millimeter aluminum filter which transmits a broad range of Bremsstrahlung radiation. And this same figure will also show a gadolinium filter of 0.2 millimeters thick, and this gadolinium filter, if you see here, there is increased number of photons in gadolinium filter are seen from around 25 kilo electron volts to 50.2 kilo electron volts. So there is increased number of photon energy is photons are seen from 25 to 50.2 kilo electron volts. That is gadolinium mass attenuation coefficient decreasing from 25 to 50.2 kilo electron volts. Immediately above 50.2 kilo electron volts, mass attenuation coefficient of gadolinium increases dramatically. Then and the number of transmitted photons corresponding to above 50.2 kilo electron volts is also diminished. So you can see that the heavy metal filter transmits a narrower spectrum of energies than the aluminum, which transmits broad Bremsstrahlung radiation. So this is about the Bremsstrahlung radiation by aluminium and characteristic radiation by gadolinium. We have one more image which shows photon energy on x-axis and the attenuation coefficient which is in log scale on y-axis. So this figure shows the mass attenuation coefficient of iodine compared with holmium. So we have two things, iodine and holmium. So we have to draw. So if you see the the attenuation coefficient of iodine dramatically increases at around 33.17 kilo electron volt. So this is 33.17 kilo electron volt where the attenuation coefficient of iodine increases dramatically and then decreases with an increase in photon energy. The attenuation coefficient of iodine increases dramatically at 33.17 kilo electron volt and then decreases with increase in photon energy. Similarly, we can draw a similar graph for holmium at 55.6 kilo electron volt. So the attenuation coefficient of holmium steadily increases from 33 kilo electron volt to 55.6 kilo electron volt, at which point the attenuation of holmium increases dramatically at this 55 kilo electron volts. So the important concept is this overlap window which is in the range of 33 to 55 kilo electron volt. In this window, the high transmission between the 33.5 and 55.6, that is in this window, high transmission of holmium filter overlaps the region of high attenuation of iodine filter. There is attenuation of iodine is seen maximum at 33.5 to 55 kilo electron volt, and attenuation and the transmission of holmium is high between 33.5 to 55.6 kilo electron volt. This is the overlap window which is about 20 kilo electron volt that affords improved contrast when imaging iodine or barium when the X-ray beam filtered by heavy metal filter is compared to that of aluminium filter. So this is holmium, this is iodine. So if I'm drawing the same picture again because it's not good. So the K edge of, okay, so this is the overlap window that is between 33.7 to 55.6 where the iodine has maximum attenuation and holmium has maximum transmission. So the overlap window of around 20 kilo electron volt affords improved contrast when imaging iodine and barium when the X-ray beam filtered by heavy metal filter is used here when compared to aluminium filters. So overlap window of around 20, that 20 kilo electron volt, that is between 33 to 55 kilo electron volt, causes high transmission of holmium filter, overlaps the region of high attenuation by iodine, high transmission of holmium and high attenuation of iodine. So this is the same diagram drawn again because this is better diagram. So these are the important points about KH filters. Thank you.